Here we are looking at the left side of x naught. Here we are looking at the right side of x naught. If x naught is an adherent point of this set, we define the right limit of f at x naught by this. Provided the limit exists. Now let us briefly go back to the definition of limits in general, and let's see how this is a special case of that itself. Yeah, we can of course see that because these are after all limits, but let's again go back to that definition. What was the actual definition? In that definition, we had a subset E of x, which itself is a subset of the set of real numbers. F was a function with x as its domain, and it was real valued, of course. We are only considering real valued functions. What else was there? X naught was a point in the closure of E, or in other words, x naught is an adherent point of E. And there was one more thing, a real number L. We then say that L is the limit of f at x naught in E if something happens, right? There was that actual definition involving epsilon and delta, we know that. But let us concentrate on the notation. When the limit exists and is L, we then write this, right? What is our E in this case? Here, for example, the E is this set. Okay. Is this E a subset of x? Yes, of course it's a subset of x because it's the intersection of x and some other set, which is some interval. And x naught is an adherent point of E. I mean, it was there, we don't have it right now. And if the limit exists, then we say, in this case, this L is the left limit. Then we call that special limit the left hand limit or the left limit of f at x naught. Okay, and similarly the right limit also. Now, if we go back to the equivalent formulations of limits, one can see that we can bring in that sequential thing here also for left and right limits like this. So what that sequential thing tells us is Yeah, we had it in proposition 947. So by proposition 947 we can say things like this. Say you have the whole setup, that is there is f, there is x and all those things, and suppose the right limit exists at x naught. So this thing exists and we already have seen what this is. Okay, so the right limit, that means this limit exists. Then by proposition 947 if you find a sequence of points in this set that converges to x naught, then the functional values of the sequence terms will also give you a sequence. That sequence then by this proposition has to converge to this. If an is a sequence in x for which all the terms also lie in this interval, for which an is greater than x naught for all natural numbers n, that converges to x naught. It is not any sequence in this set but a sequence that converges to x naught. Then this sequence f of an converges to the right limit of f at x naught. A similar statement can be made for the left limit also in case it exists. But let us now see one example. Actually this discussion comes after the example, but I am saying it now itself. So in this example we go back to our familiar signum function, that thing which gives us, if you want to say so, the sign of a real number. Let's recall that. And I think for some reason I am already running out of ink. I think I forgot to refill this. Okay, so let me just do that now. Actually the rainy season is no longer here now, so things are drying up very quickly. So the function was just this, and we saw it for the first time in example 9.3.16. The definition of it is just this: it's constantly 1 if the input is positive, is 0 if the input is 0 and it's constantly minus 1 if the input is negative. Okay, so this is the function. Now say we want to calculate the left limit of this function at 0 if it exists. Let's see, that is, we want this. Then by the definition we would have to calculate this limit. What is the x here? The domain R. We have to intersect it with the, I am considering left limit, so the left side of 0. Now this intersection is just that interval itself because this is the subset of R. But in this region, the function is constantly minus 1 because we are only considering the negative real numbers. So we are getting this, which of course is minus 1. So the left limit at 0 in fact exists and it is minus 1. Similarly, the right limit at 0, if one calculates it, one would get plus 1. You can pretty much see why, because of this part of the definition. And the value of the function at 0 of course is 0. So we see that these three values exist, but they are all distinct. They are different from one another. And one should also note, okay, see, here the point at which we are calculating the left limit and the right limit, that point is a point in the domain of the function. That, however, is not necessary. For example, you consider this function. And the function is defined by this formula. You can understand why we have removed 0 from R, because otherwise this is not defined. Then what can we say about the left and right limits of this function f at 0? Note one more thing, that the moment you say this, that I want to calculate the left limit of a function at a point, keep in mind that the point should be an adherent point of that set that we have in the definition of this one-sided limits. Is it, by the way, was it the case here in this previous one? Let's see that also. So what we are doing here is that we are trying to calculate the left limit of SDN at 0. However, before we go through the calculation, we should actually have made sure that 0 is an adherent point of this set. Is it true? This set turns out to be just this interval. Yes, that is true, because we have already seen in a previous section that the closure of this interval is this interval which is closed on this side. So 0 in fact belongs to this, and so 0 is an adherent point of this. But 0 was also a point in the domain. That is not the case here. However, this part must be first of all seen, okay, properly, whether we are getting that point, a point in that set that needs to be considered in this one-sided limits. Say we want to think about this. We then want 0 to be an adherent point of what set in this case? 0 needs to be here. This is our x intersection 0, plus infinity. 0 needs to be in the closure of this set. Is that the case? You see that just like this intersection is this interval, this intersection, although we have minus infinity 0 here, but you can understand that had we shown the full calculation of this, we would have considered such a thing with r in place of this. You can see that since 0 belongs to neither this interval nor this interval, not this set, this interval is actually a subset of this, and so this intersection is nothing but this interval, and the closure of this interval is of course this closed ray, and 0 belongs to this. So yeah, we can talk about this at least. We can start talking about this. Now let's see what it is. So if one starts calculating this, x belongs to, because we have already seen how it looks, so we can just directly write this f of x because x is positive, so the absolute value is x itself, which is why this will become constantly 1 regardless of that actual value of x, and so it is 1. Similarly, this will be minus 1. So here also the one-sided limits exist at 0. However, unlike the previous SGN function, 0 now is no longer a point in the domain. The function itself does not have any value at 0. And if you look carefully at the function itself, it is in fact a part of SGN. From the definition of SGN, if we remove 0 from the domain of SGN and modify the definition of SGN like this, then you will see that they are matching. Why? Because to the right of 0 in that region, the denominator is x, so ultimately it's just constantly 1. Whereas to the left of 0 it is minus x, so it is constantly minus 1. So the point here is that the point need not be a point in the domain of the function. Okay, now let us leave limits and let's go to continuous functions. Say we have a function f from x into r, where x is some subset of r, and suppose that x naught is a point in x. If you go back to the definition of f being continuous at x naught, that means what? It means that this limit exists and is equal to the value of the function at x naught. When this happens, we say that f is continuous at x naught. Okay. Now, can we, in this case, think of left and right limits of f at x naught? Let's see. Okay. First of all, but before thinking about that, or before trying to calculate them, if they exist, let us make sure that x naught at least satisfies that condition, that it is an adherent point of that set. What happens to this statement, for example? This statement, say, is it true? Well, if you go back to the section where we discussed these closures and use properties of closures of sets and their intersection, you will see that yes, this is actually true. Note one thing, that x naught is an element of x itself, and so x naught is an adherent point of x as well. That is, x naught belongs to the closure of x, and also x naught is an adherent point of this interval, because the closure of this interval is the interval closed x comma open infinity. From these two pieces of information, you will be able to show that yes, x naught belongs to this closure as well. Alright. Now, what we want to claim is this, that we want to claim this, or in other words, what we are trying to claim is that the right limit of f at x naught is equal to f of x naught if the limit of f of x is f of x naught at x naught. And in trying to show this, we are not going to show this, I will use that sequential formulation of continuity, or sequential formulation of limits actually in the background. So, trying to show that this limit exists and is equal to f of x naught, if I use sequences, what should I do? I should take any sequence in this set that converges to x naught, and then I see the functional values of the sequential terms and see where that sequence converges, or if it converges at all. So let me take an arbitrary sequence an, okay, here in this set, such that an converges to x naught. Then an in particular is also a sequence in X that converges to X naught. Why? Because this is a subset, this intersection is a subset of X. But we already have this limit. So by the sequential formulation of limits, I have immediately this thing. However, the sequential formulation works both ways. Okay, it's an equivalent condition for a limit to exist. So what we have ended up showing is that for any sequence of points in this set, this intersection, the functional values form a sequence that converges to f of x naught, provided of course that the original sequence converges to x naught. So by the sequential formulation again, this limit exists and is equal to f of x naught, or in other words, that the right limit of f at x naught exists and is equal to f of x naught. Okay, so if the function is continuous at x naught, then the right limit exists and is equal to the functional value at x naught. And you can clearly see that you can similarly show that the left limit of f at x naught also exists and is equal to f of x naught. So from this same condition that f is continuous at x naught, we get this as well, that the left limit at x naught exists and is also equal to x naught. That means continuity implies existence of left limit and right limit, and both of them are equal to the functional value at that point. But the converse is also true, and with this, that is important, and that is this next proposition. Proposition 953. So what the proposition says, of course, is just this. Let me just write the main things. So x is a subset of R. F is a function with x as domain and R as range. And let x naught be a point in X. Suppose that x naught is an adherent point of this set and x naught is also an adherent point of this other intersection. Also, let the one-sided limits of f at x naught exist and be equal to the functional value at x naught. Okay, so in other words, or in short, the two-sided limits exist and they are equal to the functional value at x naught. Then f is continuous at x naught. The ceiling fan of this room is making a lot of noise. I need to get it repaired. Okay, I will do it soon. I hope it's not a very big problem. Then f is continuous at x naught. So let us now see the proof. The proof is given in the text. So let us first write what the things are that we are given, what we have. For the sake of simplicity, the author is denoting the functional value at x naught by L. So this is what we have. This is equal to L. The right limit of f at x naught is L, and the left limit at x naught is L as well. Our aim is to prove that the limit of f at x naught is L, but the set over which we will vary our independent variable is no longer any of these intersections, but the entire x. That's what we want. So let us choose epsilon greater than 0. The text has not used the sequential formulation of limits. If you want, you can use. I think in that way also one can approach. But anyway, here we need to consider epsilon and delta. So now let us forget about one-sidedness of these limits. These are, after all, fine. They are one-sided limits, but actually at their heart they are just limits, right? So for this epsilon greater than 0, we are going to get delta 1 and delta 2 for these two limits. So there exists a positive delta 1 and a positive delta 2 such that, now we just use the definition of limits, the distance between f of x and L will be less than epsilon for all x belonging to this intersection, this satisfying this inequality. Satisfying this inequality, that the distance between x and x naught is less than delta 1, and now we are going to write for this limit. We also have this for all x belonging to the left side of x naught in x, satisfying this delta 2. We understand why these are the way they are. They are coming because of these two limits. Now let delta be the minimum of delta 1 and delta 2. Okay, so the first thing we note about delta is that it is also positive, just like delta 1 and delta 2. But why? In fact, the author has explicitly asked why. That's because this is either delta 1 or delta 2, and both of them are positive, so it's also going to be positive no matter what the case is. Now consider any point x in x such that the distance between x and x naught is less than this new delta, then x belongs to x and x belongs to, you see, satisfying this inequality is equivalent to x belonging to this open interval, right? X naught minus delta comma x naught plus delta. Now two cases arise. Well, there are actually three cases. One of them is almost trivial, but let's write that also. Let's handle that first. Now x belongs to this open interval, so x may either be equal to x naught, or x may lie on that side of x naught, or x may lie on this side of x naught. So let us first consider the case where x is equal to x naught. If x is equal to x naught, then what happens to this difference? Then f of x is f of x naught, however L itself is f of x naught, so this is 0, which is less than epsilon, because epsilon is positive. If x is greater than x naught, okay, that means x lies in that part, it lies in the open interval x naught comma x naught plus delta, then x belongs to this. Do you see why? X is already coming from x, so of course x is in x, but being greater than x naught, of course less than x naught plus delta as well, but we need not consider that part. We just consider the fact that x is greater than x naught, and as a result x belongs to this open interval as well. So that's why it belongs to their intersection. And additionally, the distance between x and x naught is less than delta, fine, but because delta is the minimum of these two things, okay, so delta has to be less than or equal to delta 1. Why though? You see, delta is either delta 1 or delta 2. When will delta become delta 2? When delta 2 is the minimum of these two, that is delta 2 is less than or equal to delta 1. In that case delta is equal to delta 2, but then delta 2 is less than or equal to delta 1. So we are going to have this, and if delta 1 itself is delta, then we have equality. So in any case we are going to get this. But now you look at this part. Whenever x comes from this set and it satisfies this inequality, which it is satisfying here, then the distance between fx and L is less than epsilon. And so okay, so in this case also we are getting this fact. And if on the other hand x is less than x naught, now I think you already can see what I am going to write. If x is less than x naught, then similarly x belongs to this intersection and the distance between x and x naught is less than delta, and similarly delta, just like it is less than or equal to delta 1, it's also less than or equal to delta 2. And so that means regardless of what x is, in what part of this interval x lies, we will always have this. Hence, in any case, so what have we shown? We have shown that for our arbitrary choice of epsilon, which is a positive real number, if x, we have found a delta, okay, which is this delta, so that any point of capital X which is within a distance delta from x naught gives us this inequality. Hence, the limit of f of x as x tends to x naught in x, because we are choosing x from x, exists and is equal to L, and L is nothing but f of x naught, and that is why f is continuous at x naught, and that's where the proof ends. You can of course clearly see that this left and right limits being equal, and they are implying that the function is continuous, has a limit version as well. If in general left and right limits are equal to a common real number, then that real number turns out to be the limit of the function. So that result is also similarly true. Here, however, more specially we are concentrating on continuity rather than just simply limits. Okay, so that is this result. But after this there are some other discussions also. I need more ink. The section is over, but there are some discussions on the cases where f is not continuous at x naught. By definition, continuity demands that the limit of the function exists at x and be equal to the functional value at x naught and be equal to the functional value at x naught. But now that the situation has been broken up into these one-sided limits and continuity is being equivalent to their existence and their equality to the functional value, we can now look at several different cases. That is, we are now going to look at the ways in which this does not happen. Okay, and that will give us a way of classifying instances where f is not continuous. How does that work? It may sound like an unnecessary thing to do. If a function is continuous, well, fine, it is continuous, and we know that continuous functions have nice properties. But if a function is not continuous, why bother to study it further? Because it does not have many nice properties that the continuous functions have. But even in such case also, many things are there to consider. So that part of the discussion goes like this. In fact, the author says, let me just read it out. As we saw with the signum function, it is possible that both the left limit and the right limit at x naught exist, but are not equal. We have seen that the SGN left limit at 0 is -1, but the SGN right limit at 0 is 1. and they are not equal. So that immediately tells us that the SGN function is not continuous at 0, because by what we did before this proposition, we know that if a function is continuous, then the two-sided limits exist and are equal, and the proposition provides its converse too. So the SGN function having different one-sided limits immediately tells us that it's not continuous at 0. And when this happens, we say that a function has a jump discontinuity. You see, if you draw the graph of the SGN function, the term needs to be justified also, no? We can draw the graph of the SGN function. It's not that difficult. So this is our positive x-axis, positive y-axis. Say we roughly mark out 2 points. So this is 1 on the positive y-axis, this is -1 on the negative y-axis, and in between we have 0. So the SGN function definition tells us that its value is constantly 1 if the input is positive, which means that a part of the graph is this. I am using this, you probably already know this, I am using this white circle to indicate the fact that this line never reaches the y-axis. In order to keep it apart from the y-axis, we draw like this. Similarly, when our input is negative, then the graph is this. This line also never reaches the y-axis. You should understand that although I have drawn these circles quite big, but these circles are they do not have any radius. Okay, they are just there to indicate that these lines do not touch the y-axis. It's not that inside this circle there is a region in which there is no graph on that side and here on this side. No, it's not like that. They just are there to prevent these lines from reaching the y-axis, because at 0 the SGN value is 0, and at that 0 it cannot have any other value, because then it will not be a function at all. So this is how the graph looks. The graph has 3 parts. One is this straight line, one is this straight line, and here is this isolated point also. That is also a point on the graph. So the situation here is this. This is -1, which is not equal to 1, and 1 is the right limit of SGN at 0. So it's not continuous at 0, and there is a sudden jump in the graph as it crosses, as the input crosses 0. So that's why the discontinuity, which is the point x equal to 0, is called a jump discontinuity. Okay, but there are other ways in which functions can be discontinuous. The next function the author considers is also one that we have already seen. It is this function. f from R into R, and it is also partly defined, but its definition is this. The function is, it takes the value 1 if the input is 0. Okay, and it takes the value 0 if the input is non-zero. And if you draw its graph, then you almost won't have to draw anything. You just draw the x-axis, the y-axis, and then you can see that at the non-zero inputs the functional value is 0. So the graph is almost it almost lies on the x-axis itself, except at this point. Okay, so just like these lines, here also the graph consists of this line, that is, a part of the graph is the x-axis from which the origin has been removed, and in place of this there is this single point which is 1 or 0 comma 1 if you want to write the coordinates. So what about this function? If one tries to think of the left and right limits at 0, one will then quickly realize that the right limit is 0 and the left limit is also 0. So in this case the right and left limits exist and they are equal, not like this case. But still the function fails to be continuous because they are not equal to 1, which is the functional value. It is another kind of discontinuity, and it's called a removable discontinuity. Why? This name also has a reason. You can redefine the function slightly differently. This function takes the value 1 at 0. In place of this, you can define another function which takes the value 0 at 0, so that it is constantly 0. So that other function is exactly like f, except at x equal to 0. So that way, if instead of this function you consider that other function, by redefining the value at 0 and thus removing this discontinuity, you will then get a continuous function. That's why it's called removable discontinuity or removable singularity. A singularity is a point, roughly speaking, where things break down. Okay, in mathematics it has specific meaning, but in general also it's used elsewhere. So this is another kind of discontinuity. But there are other ways also that a function can be discontinuous. Let's before we present another case, let's see what has happened so far. Regarding discontinuity. The two-sided limits exist, but they are not equal. That is one kind, jump discontinuity. The two-sided limits exist and are equal, but they are not equal to the functional value at that point. Removable discontinuity or removable singularity. However, the two-sided limits themselves may fail to exist, so that is another case. For that, we need to just consider this function. F of x is 1 over x. That is the ordinary reciprocal function. If you draw the graph of this, you know how the graph looks, rectangular parabola. What the hell am I saying? Rectangular hyperbola. Roughly, it looks like this. The nature of the graph is that as x, and let's just talk about the positive inputs, okay. As the input increases, the output decreases, but still stays positive. That's because the reciprocal of any positive real number is positive. But the more the denominator becomes, the less the value becomes. And the exact opposite thing happens when you make x very close to 0 but still keeping it positive. Then the value increases without any bounds. That is indicated by the graph shooting up like this. And a similar effect is seen on this side also. The only difference is that as the independent variable gets close to 0 while always being negative, the absolute value of 1 over x increases but with a negative sign, so it goes down without any bound. And a similar effect also is seen on this side as x approaches minus infinity. Okay, so this is how the graph looks, and in this case these limits do not even exist. So how can the function be continuous? Because continuity demands, we have just now seen that both the limits exist and they be equal to the functional value. And this kind of discontinuity also has been given a name by the author, or it's a standard term, I don't know. Okay, asymptotic discontinuity or singularity. Is this the only way in which one-sided limits don't exist? That is by the values being unbounded? No. The values may be bounded, but still the limits may not exist. And this example also we have come across. Actually, this asymptotic thing and this next one that I am now going to show, these fall under another item, remark 954, but there is no need to write that. So this final function is also one that we have already seen. It is a very badly behaved function, a pathological function from analysis point of view. It takes the value 1 if x is a rational number, and it takes the value 0 if x is an irrational number. We have keep in mind that we have already seen that the limit of this function exists nowhere. This we have already seen, and as a result the one-sided limits also do not exist. But still the function is bounded. It does not have this kind of behavior. It is so bad and pathological. I am saying, I am using this term because you cannot even attempt to draw any graph. So this is another kind of discontinuity, oscillatory discontinuity. Roughly speaking, here the function is discontinuous at any given point x naught, because as your independent variable x approaches x naught, the functional values oscillate between 0 and 1 so much that it never settles anywhere. So that's why it fails to have any limit. And lastly, the author mentions that the study of discontinuities goes way beyond this simple considerations, and particularly in complex analysis we see this in its full form, where we classify also discontinuities or singularities that are isolated into removable singularity, pole, essential singularity, those things. Here, however, we won't discuss those things. They are beyond the scope of this text. So that's how this section ends. So in the next analysis update, of course, we will see the exercises. So it will be in the community section. And our next upload is this coming Tuesday, and on Tuesday let's go back to field theory once more. So with that, I sign up for tonight. So see you on Tuesday with field theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.